We typically look at soils and think of the properties of the soil mass. But it is important that we recognize that soils are made of grains. Therefore, I invite you today to imagine a grain and to identify the most important characteristics of the grain, because those particle scale properties will upscale to determine the behavior of the soil. And so when we think of grains, probably the first thing that comes to mind is size. But then we imagine a lentil, a navy bean, a penny, a marble, and we realize that shape is also very important. We tend to think that color is important, but actually it is quite irrelevant, except for the fact that color is telling us something about the composition. And so many properties of the grains will depend on the mineralogical composition. There is one property that we'll come back to discuss, which is specific surface. Finally, we could think of a large number of other properties. A very important one is the specific gravity. We could also think of the thermal conductivity of the grains, which will upscale to determine the thermal conductivity of the soil. We could think of the dielectric constant of the grains. For example, if you are trying to do ground penetrating radar, that will be important. Now, what I would like to highlight here is that all the properties, but in particular these three, and everything else will follow, are totally dependent on the genesis of the soil. For example, coarse-grained particles, like sands and gravels, are the result of mechanical processes. However, fine-grained particles, the phyllosilicates, the clays, some precipitates like small crystals of pyrite and calcite, they are actually precipitates. In other words, they are the result of some dissolution and reprecipitation processes that take place in nature. And as you can see, there is an intimately related shape associated to that. The large particles mechanically generated will tend to be rounder. The finer particles will tend to have the clear shape of crystals or platiness, like clays. And as we are talking about this, you begin to realize that the mineralogy has also changed from, let's say, the silicates, the quartz, the carbonates for the coarse grains, to the calcites, the pyrites, the phyllosilicates that make clays. And so genesis will determine size, shape, mineralogy, and all other properties related to soils. To summarize, we can put on an axis the different sieve numbers, which is in this case the sieve number 200 and the sieve number 4. And if we think of the sieve number is how many wires we put within 1 inch, so 25 millimeters divided by 4, and if we account for the wire number, this is 4.7 millimeters. And if we divide an inch by 200 and we subtract the thickness of the wire, this is the typical 75 micrometers. And in this case, we have the silts and the clay size. In between here, we have sands. And coarser than that, the gravels. So mechanogenesis works very well for the coarser grains and loses effectiveness as the grains get smaller and smaller because they don't have enough momentum to crash against each other and to break particles. So mechanogenesis begins losing relevance below 10 microns, and then this is the regime where it works. Now, the finer particles are all precipitates, and that is the importance of aqueous chemistry. In other words, there must be water. Therefore, for example, we can go to other planets and think if there are clay minerals, then there was water. So these are going to be precipitates. So chemogenesis. Now, there are other mechanisms in between. For example, fly ash is going to be in this region of a few microns, and that is thermogenesis. And in addition, there is a big range of sizes that are bio-created, bio-mediated, and for example, all the shells. But in particular, I would like to highlight the diatoms and foraminifera in the micron, submicron, and larger sizes. So this will be somewhere here is the biogenesis. To summarize, the history of the sediment determines so much: the size, the shape, the mineralogy, and all other properties that are related to these characteristics. So let's explore size a little bit further. And because there are so many grains in a soil mass of interest, we're going to use some statistical summaries. Notice that when we have statistics, like for example, the height of people, we are going to have some type of a Gaussian distribution where this is height and these are number of individuals. Now, instead of presenting the density function, I could also plot the cumulative version where this will be 100% of the individuals. This is 50% of the individuals. And by the time I begin accumulating, this is going to look something like that, where I go through 50%, where the 50% of the distribution is. So this is the cumulative version. This is the density function. And typically, the way we summarize these statistics is that this is the mean. To the distance to the point of inflection is the standard deviation. And the only thing that I would like to add at this point is that certain quantities really don't look like that, but they look with a skewed distribution. It looks like that. In other words, there are no values negative that are negative, less than 0, including heights. And so these type of distributions, I could also take another measure of skewness, but in some cases, if instead of plotting, let's stick to h, if instead of plotting h, I plot in the logarithm of h divided by the unit of h, in order for me to extract the logarithm, then it may be that I stretch the little ones, I contract the big ones, and this looks Gaussian in the logarithm of the scale. If that is the case, I'm going to say that this quantity is log normal distributed. And most physical quantities really are not Gaussian distributed because they don't have a negative value, including grain size. So consider all this as a prologue to the following observation. When we plot grain size, we plot it versus the log of the diameter divided millimeters, let's say. Could be any unit that we choose depending on the soil. And this is 100%, but we do it in terms of the percentage of the mass passing a certain sieve, cumulative mass. And the distribution looks something like that. But by tradition, we haven't taken the mean as a meaningful value. This would have been the diameter corresponding to the 50%. But actually, we take the diameter corresponding to the 10%. So this is the 10th percentile, and this is the D corresponding to the 10th percentile. Sometimes we also pay attention to the 60th percentile. And so this is diameter for 60th. And we could take another intermediate value. For example, this would have been for 30. Furthermore, we do not report the mean value and the standard deviation, which I could have obtained. Probably for this case, the standard deviation could have been like that in a log normal distributed size. We do not report the mean and the standard deviation by convention. Instead, we pay attention to these three values most of the times. And so we talk about the D60 of the soil, the D10. We don't refer to the standard deviation, but we have defined two other coefficients, the coefficient of uniformity being D60 divided by D10. Is the ratio between this and that is a little bit telling us something about the standard deviation. But it could be that these 2 points with the same D60 and the same D10 could have a curve that looks like that, or actually a curve that would have been convex versus concave. And so the D30 tells us a little bit about the convexity or concavity of the distribution. So we use the coefficient of uniformity D30² over D60 times D10 to capture the statistics of our grain size distributions. We are actually doing statistics. And instead of choosing this type of convention of classical statistics, we have developed our own summary of the statistics. But we are doing a statistical summary of the grain size distribution of a soil. Grain size distribution is very important for how grains pack and form the granular skeleton. But shape is equally important. In the simplest choice of words, we can think of eccentricity angularity and roughness. But we could also think of the opposite terms. So this would be sphericity roundness and smoothness. Let's try to see how they would manifest. This is a spherical particle that is smooth and is not angular. Therefore, it has high sphericity, high roundness, and smoothness. With respect to this particle, an eccentric particle may be like this one, where the particle has deviated from the spherical shape. With respect to the spherical particle, an angular particle would be like that. And once again, with respect to a spherical shape and smooth sphere, a rough particle would manifest almost like the teeth around a coin. From this point of view, if we focus on the shape of the particle in any given direction and we measure the radius of the particle in direction theta, where this is the angle theta, then we come here and we realize that at 0 degrees we have lost some of the radius, but we have added it at 90 degrees. And we lose it again at 180, and we gain it again at 270. So if I were to stretch the particle radius versus theta in a linear axis, then we would see the waviness of 2 cycles of a sinusoid, where this is the amplitude there. So while the radius in all directions is equal to the radius r, in this case the radius is r, in this case the radius in direction theta will be equal to r plus a certain amplitude of the deviation times cosine 2 theta. In other words, there are 2 cycles of a sinusoid. In this case, we don't have 2 cycles. We have many cycles, probably 10 or more. So here we have approximately 2. Here we have approximately 10. And in this case, we have approximately 100 cycles of a sinusoid riding over. So now we can identify particle shape as a Fourier series, whereby the low frequency components define eccentricity, the intermediate frequency components define angularity, and the high frequency components determine roughness. Therefore, you will see many algorithms and publications and software for image processing that use the Fourier transform to determine the key parameters for particle shape. But now you can begin inferring many things about particle shape. For example, eccentricity will determine particle alignment. When you shear, the particles will go flat. For example, imagine that you are shearing rice. The grains will rotate and will go flat. So this one will determine alignment. During shear. But what about angularity? Where angularity is like the knuckles between your hands, is the one that locks in the rotation of one particle with respect to the other one. So this will determine friction. And dilation. And now what about roughness? Roughness, imagine that you have another particle here that is also rough. Roughness is really the one that is going to control how much those contacts deform, even at small strain. So roughness will have a very important effect on the small strain stiffness. So as you can tell, particle shape will affect all our properties: the orientation and the residual friction angle, the peak friction angle between friction and dilation, and some small strain properties. Of course, roughness also affects the large strain behavior. But roughness will give me lower stiffness, even though it gives me higher shear strength. The third property that we should pay attention at the level of the grains, but that will also be valid for the whole soil mass, is specific surface Sometimes we use this term, but the proper thing is specific surface area. And specific means that it's a ratio of the surface area with respect to either the volume of the mass, so surface area divided the volume. Now, if we do it like that, then this will be meter squares. This is meter cubed, and the ratio is 1/meter. That is typically reported in many areas, like, for example, in the earth sciences. I find that it has a little bit more physical meaning if I multiply here times the mass density of the mineral, so then the units become meter square, and volume times specific times mass density gives me grams. So this will be meter squares per gram. And this is very meaningful. If I say that I have 10 meters squared per gram, you can visualize a gram of soil, which is probably, it will fit in the tip of my thumb, and that has 10 meter squares. That's quite impressive. That is, for example, the case of kaolins. And so, why is this so important? Because there are many processes that are related to activity on the surface, and many factors that are related to the volume or the mass of a particle. For example, the self-weight is mass, but all the chemical reactions that occur are surface related. So this ratio tells me the balance between surface related forces over gravimetric or volumetric related forces. And I would like to emphasize the importance of this variable in understanding soil behavior. So we're going to do some computations in the spirit of learning something important about specific surface. So let's start with a few examples. Imagine that we have a cubical particle, and that cubical particle is of size L. Therefore, the specific surface area is equal to L squared. This is the size of one surface, and we have 1, 2, 3, 4, 5, 6 over the volume, which is L cubed, times the mass density of the mineral that makes the particle. So this is going to be equal to 6 over length, the length scale of the particle, times the mineral mass. Let's see, for example, what would happen if I take exactly the same mass, but I manage to split this particle in along this plane and also along the horizontal plane. And I do one more cut. So now instead of having 1 cube, I end up having 8 cubes. Now I have the same mass, but notice that I have added 1, 2, 3 cuts. Each of them generated a surface above and below, or left and right. Therefore, I have added 6 more surface areas, 6 more surfaces, L squared. However, I haven't changed the mass. Well, this is telling me that indeed, the smaller the size of the particle, the higher the amount of surface that it will have, specific surface area. Let's take another example, platy particles, typical for clays. And so we're going to make a simple geometry, which is not the geometry of clays, which, for example, is more hexagonal. Let's say that this is L times L. For simplicity, I'm going to say that the thickness is much smaller than the length of the particles. So all the surfaces contribute by the upper and the lower areas. So the specific surface is equal to 2L squared over L squared T times rho mineral. The L squared cancels out, and this is 2 thickness times rho mineral. And now I can reach one more conclusion, that the specific surface area is inversely proportional to the size of the particles, but furthermore, is inversely proportional to the smallest dimension of a particle. So this will have a very high specific surface area. And now we can generalize it, for example, for a cylinder. If this has a diameter r and a length L, then the specific surface area will be equal to 2 pi r L, which is when I unfold the cylinder. And once again, I'm going to assume that r is much smaller than the length. So therefore, pi r squared, which is the area of the two end caps, will vanish with respect to that quantity. And then I do need the pi r squared, which is the base times the height, to get the volume times rho mineral. And now the pi r with r, L with L, and this is 2 over r rho mineral. Once again, the smallest dimension of the particle determines the specific surface area. I invite you to extend this to do a few computations. For example, what is the specific surface area for a cubical particle if the length is 1 micron? Or what would be the specific surface area of a platy particle when the thickness is 9.6 angstroms, which is a montmorillonite? And you will see that from this analysis, you will conclude that you have approximately 2 meters squared per gram for a micron-sized particle, and that you will have 720 meters squared per gram for a bentonite. For a kaolin would be a similar analysis, and you will conclude that you have somewhere between 1 and 10 meters squared per gram for kaolins. Let's understand the implications of that. If I were to put side by side 1 gram of bentonite, which is really the amount of the tip of your finger worth of bentonite, then I would cover an area 720 square meters. Well, divided by 2 because I will have the upper and the lower surface, but still it's a very large area. So not surprisingly, many materials that we use every day, like for example, latex paint is loaded with kaolin. That's the reason why it's so important to shake it very well, because it tends to sediment while it's waiting at the store. Toothpaste have clays. All the plastic that we use in our cars and in our homes are loaded with clays to strengthen their properties. And the main reason is because surface-related forces become so important when the specific surface area is high. This will also tell us that in soils where hydromechanical effects are always coupled, those couplings, for example, the chemical and the hydraulic and the mechanical, will be more important when the surface area, the specific surface area, is high compared to when it is small. Therefore, they will manifest in the clay soils and almost no effect on the coarse-grained soils. To summarize, we were looking at the grain scale properties of soils, and we realized the importance of size and shape. Mineralogy will be critical because it will determine the surface charges and the abrasiveness and the hardness of the particle. Remember the Mohs scale of hardness, from talc to diamonds, and it will determine the hardness of the particles. By the way, there are 6,060 minerals recognized by the International Mineralogical Society. And we only tend to deal with a few in our professional practice, or mention a few, but each of them has unique properties and characteristics. And finally, the importance of a specific surface area, because it will tell us the relevance of surface-related forces with respect to gravimetric forces. And let me give you a hint. This is the importance of the liquid limit. It's going to be picking up these effects.